On November 3rd, 2025, an interstellar object designated I-1SAR 2025 U1 made its closest approach to Venus. Astronomers had monitored it for months, anticipating a routine flyby as it sped toward our solar system at 26 kilometers per second. However, its behavior defied expectations, sparking intense scientific debate. As the object neared Venus, telescopes detected unexpected acceleration and erratic brightness fluctuations. If that idea gives you chills, you're exactly where you're supposed to be. Hit like, subscribe, and drop a comment with your theory. And if you want this story to reach others who still believe in questions, share it, X, Facebook, Reddit, or your group chat. You're helping light up the dark. Thank you for being part of this. Its trajectory diverged from predictions, and natural explanations like solar radiation or outgassing couldn't fully account for these anomalies. Some researchers proposed a bolder idea, that the object might be something far more enigmatic, challenging our understanding of interstellar visitors. The scientific community was divided. Teams at the International Astronomical Union analyzed spectroscopic readings and trajectory models, but the object's true nature remained elusive as it journeyed onward. Public speculation ranged from alien technology to unknown natural phenomena, fueling a trail of questions. This encounter was more than a flyby. It was a cosmic event poised to redefine our place in the galaxy. The data collected near Venus may unlock mysteries of interstellar travel, whether natural or artificial. For astronomers, it underscored the vast unknowns beyond our solar system. For the rest of us, it rekindled curiosity about the universe and our connection to it. As I-1 2025 U1 vanished into deep space, its legacy endured. It left more questions than answers, but ignited a renewed drive to study interstellar objects, which could offer insights into planetary formation, distant star chemistry, and even the possibility of life beyond our solar system. The encounter marked a turning point, a moment when humanity's curiosity reached for the stars, eager to unravel their secrets. Part 1. The Visitor. What if an object from beyond our solar system passed by Venus and left us with more questions than answers? On November 3rd, 2025, 3I Atlas, the third interstellar visitor in human history, did just that. This traveller from another star system had a mottled surface of reddish and grey hues, unlike anything in our solar system. Spectroscopic analysis revealed rare elements, hinting at origins in a distant star system. Its surface reflected light, in a way that suggested it might be coated in a thin layer of material, perhaps a remnant of its formation or a byproduct of its journey through the interstellar medium. The reddish hues in particular could indicate the presence of organic compounds or minerals exposed to intense cosmic radiation over millions of years. Interpretation. 3I Atlas is one of only 3 confirmed interstellar objects. The first, Oumuamua, puzzled scientists with its elongated shape and unexpected acceleration as it left our solar system. The second, Borisov, resembled a conventional comet, with a visible coma and tail, making it more familiar yet still enigmatic. 3I Atlas, however, is unique. Its trajectory and features sparked ongoing debates. Unlike Oumuamua's tumbling motion and unexplained speed boost, 3I Atlas moved predictably, yet its path aligned eerily with the ecliptic plane, fueling speculation. About natural or deliberate influences, this alignment, with a deviation of less than 2 degrees, is statistically improbable for an object originating from interstellar space, suggesting it might have interacted with another celestial body or force on its journey. Observation. Detected in early 2025, 3I Atlas had an unusual brightness for its small size, just 120 meters in diameter. Its reflective surface suggested a polished or metallic composition, reflecting up to 30% of the sunlight that struck it. As it neared Venus, telescopes captured a faint trail of material, possibly fine particles shed during its interstellar journey. This trail stretched over 100,000 kilometers, yet its composition remains unknown, hinting at a slow disintegration process or the release of material from internal stresses. The trail's spectral signature showed hints of carbon and oxygen, elements common in both organic and inorganic compounds, but its exact nature remains elusive. Speculation. 3I Atlas's oblong shape and reflective surface have led some to wonder if it is artificial. Natural processes such as collisions or tidal forces can also produce unusual shapes, but the possibility of an advanced civilization's remnant, a defunct probe or fragment, has not been ruled out. If true, it would redefine our understanding of the universe. The object's shape. Resembling a flattened ellipsoid is unlike any known natural formation, further complicating the debate. Its surface features, though faint, appear arranged in patterns that some researchers have compared to structural elements, though this remains highly speculative. Known. 3I Atlas originated beyond our solar system, travelling for millions of years. Its speed upon entering was 30 kilometers per second, consistent with an interstellar origin. Its trajectory brought it closer to Venus than any other planet, allowing detailed observations. During its closest approach, it passed within 800,000 kilometers of Venus, providing astronomers with an unprecedented opportunity to study its surface and behavior. Its brightness varied significantly during this period, suggesting complex surface features or interactions with Venus's atmosphere. Unknown. Why its trajectory aligned with our planet's orbital plane and whether its features are natural or artificial. Its internal composition and the source of its faint trail remain mysteries. Some theories propose that 3I Atlas could be a fragment of a larger body, such as a disintegrated exoplanet or a comet that lost its volatiles during its journey. Others suggest it might be an artificial construct, though no evidence of technology has been found. The object's density, estimated at 2.5 grams per cubic centimeter, is higher than expected for a natural object of its size, adding to the mystery. The Pan-STARRS Observatory in Hawaii first detected 3I Atlas on January 12, 2025. Follow-up observations confirmed its interstellar nature, and it was renamed 3I Atlas by February. As it approached, its brightness fluctuated in a 7.2-hour cycle, suggesting rotation and an irregular surface. Hubble Space Telescope images revealed faint surface features, possibly craters or depressions, though their origin remains unclear. Some of these features appeared to change slightly over time, raising questions about ongoing processes on or within the object. Interpretation. Data from 3I Atlas's Venus flyby is both a treasure trove and a puzzle. Its trajectory and composition offer clues about its home star system, but its unusual features defy explanation. Some propose it is a fragment of a disintegrated exoplanet or a comet-like object that lost volatile materials. Others suggest an artificial origin, though this remains speculative. The object's reflective surface, in particular, has been compared to materials used in solar sails or protective coatings, though natural explanations such as ice or mineral deposits are also possible. Speculation if 3i Atlas is artificial, its implications are profound. Its trajectory, reflective surface and material trail could be explained by an interstellar probe designed to explore star systems. However, the lack of detectable signals has led many to dismiss this hypothesis. 3i Atlas remains an enigma, a cosmic traveler whose true nature may never be fully understood. Its journey through the solar system, observed by countless telescopes and satellites, has inspired awe and curiosity, reminding humanity of the vastness and mystery of the cosmos. As 3i Atlas continues through the solar system, astronomers are gathering data to uncover more about its composition, structure, and origin. The debate over its nature persists, fueled by the possibility that it could rewrite our understanding of the universe. Whether natural or artificial, 3i Atlas has left an indelible mark on human history, reminding us that the cosmos is vast, mysterious, and full of wonders. Yet to be discovered, its story is a testament to the enduring human quest to explore the unknown, pushing the boundaries of science and imagination in the pursuit of truth. Part 2. The Detection. Imagine spotting a single grain of sand in an endless desert. That's the challenge of detecting an interstellar object. These tiny, fast-moving specks of cosmic debris streak through the vast emptiness of space, often unnoticed, their origins shrouded in mystery. To catch one is to witness a fleeting visitor from another star system, a messenger from the depths of the universe. 3i Atlas was first identified by automated sky surveys scanning the heavens for objects with unusual trajectories. Its path was unmistakably hyperbolic, a trajectory that could only mean one thing. It came from beyond our solar system. This wasn't a comet or asteroid born in the familiar regions of our celestial neighborhood. It was an alien visitor, hurtling through the void at speeds that defied the gravitational influence of our sun. But spotting it was just the beginning. With interstellar objects, time is everything. They move fast, appearing suddenly and vanishing just as quickly. To study one effectively, astronomers need to mobilize every available instrument before the visitor slips away into the cosmic dark. The detection of 3i Atlas was a triumph of modern technology and human ingenuity. Automated surveys like the Pan-STARRS telescope in Hawaii, which scans the sky nightly for transient objects, are the unsung heroes of this story. These robotic eyes never blink, never tire, and can process vast amounts of data in real time. They are the sentinels of the cosmos, scanning for anomalies in the endless dance of stars and planets. When 3i Atlas was flagged, its hyperbolic trajectory immediately set off alarm bells. Astronomers across the globe were alerted, and a race against time began. For 3i Atlas, the stars aligned, literally. Its trajectory brought it through the inner solar system, where multiple spacecraft and telescopes could observe it under optimal conditions. This wasn't a distant flyby, barely glimpsed by our best instruments. This was a close approach, close enough that scientists could potentially detect interactions between the comet and Venus's thick atmosphere. As it passed within 37 million kilometers of the Sun, it was exposed to temperatures exceeding 160 degrees Celsius, a trial by fire that could reveal secrets hidden within its icy nucleus. Observation. The detection of 3i Atlas was a feat of modern astronomy, made possible by automated surveys and rapid follow-up observations. The urgency of the situation cannot be overstated. Interstellar objects like 3i Atlas move at staggering speeds, often exceeding 100,000 kilometers per hour. This means that every hour counts. Delays in observation could result in missed opportunities to gather. Critical data. For example, the first interstellar object, Oumuamua, was detected in October 2017, but was already on its way out of the solar system by the time astronomers turned their telescopes toward it. Its unusual shape and tumbling motion sparked endless speculation, but its brief visit left more questions than answers. With 3i Atlas, astronomers were determined not to let history repeat itself. Known, 3i Atlas was detected early, enough to coordinate an unprecedented observation campaign. Its trajectory was mapped with precision, revealing a path that would take it within observational range of Venus, the Earth, and even the Parker Solar Probe, which studies the Sun's outer corona. Unknown, whether its trajectory was purely coincidental or hinted at something more deliberate. Some scientists have speculated that interstellar objects could be fragments of distant exoplanetary systems, ejected by gravitational interactions with larger bodies. Others have proposed even more extraordinary explanations, though evidence remains elusive. But why did this detection spark such excitement? Because of where 3i Atlas was headed next. Venus, one of the most mysterious planets in our solar system. Venus, often called Earth's evil twin, is a world of extremes. Its surface is shrouded in a thick, choking atmosphere of carbon dioxide with temperatures hot enough to melt lead. Yet, recent discoveries have hinted at the possibility of life existing in its upper cloud layers, where conditions are surprisingly Earth-like. The arrival of 3i Atlas offered a rare opportunity to study how an interstellar object might interact with this alien environment. As the comet approached Venus, scientists prepared for a once-in-a-lifetime event. The encounter would occur at a distance of just 4.2 million kilometers, close enough for Venus's gravity to slightly alter the comet's path. This gravitational tug-of-war could provide clues about the comet's mass and composition, as well as the forces that shaped its journey through interstellar space. Meanwhile, telescopes on Earth and in orbit, including the Hubble Space Telescope, trained their lenses on the cosmic rendezvous. The anticipation was palpable. Astronomers had never witnessed such an event before. Would the comet's icy surface release gases as it passed through Venus's atmosphere? Would its trajectory reveal hidden properties of the planet's gravitational field? Or would it pass silently, its secrets intact? The stakes were high, and the world watched, waiting for the moment when science fiction would become science fact. Observation. The approach of 3i Atlas to Venus was not just a scientific event, it was a cultural. 1. News outlets around the world reported on the encounter, sparking curiosity and wonder. Social media buzzed with speculation as people shared their hopes and fears about what the comet might reveal. For many, it was a reminder of the vastness of the universe and the mysteries that still lie beyond our reach. Yet, amid the excitement, there was also caution. Interstellar objects are unpredictable, and their behavior can defy expectations. In 2019, the second interstellar object, Borisov, surprised scientists by displaying characteristics of a traditional comet, despite its extrasolar origins. 3i Atlas 2 might hold surprises. Its trajectory, while well documented, could still conceal unknown variables. Astronomers prepared for the unexpected, ready to adapt their observations as new data came in. Speculation. Could 3i Atlas be more than just a comet? Its hyperbolic trajectory. An unusual origin raised questions about its true nature. Some theorists suggested it might be a fragment of a disintegrated exoplanet, ejected from its star system by a catastrophic event. Others proposed it could be a natural but rare cosmic phenomenon, such as a rogue planetesimal formed in the chaotic early days of the universe. Still others, fueled by the mystery of Oumuamua, wondered if it could be something even more extraordinary, an artificial object, a relic of an advanced civilization. While such ideas were purely speculative, they underscored the profound sense of possibility that 3i Atlas represented. As the countdown to the Venus encounter began, the scientific community braced for impact. Not a physical impact, but an intellectual one. The data collected during this brief window of opportunity could rewrite textbooks, challenge assumptions, and inspire new questions. It was a moment of pure discovery, a reminder of why humanity looks to the stars in the first place. And as 3i Atlas hurtled toward its rendezvous with Venus, the stage was set for a cosmic drama that would unfold in real time, under the watchful eyes of the world. Part 3. The Target. Venus has always been Earth's evil twin, same size, same mass, same basic composition. But where Earth has oceans and life, Venus has surface temperatures hot enough to melt lead and an atmosphere of crushing pressure and sulfuric acid clouds. It's a hellish world, but its upper atmosphere is one of the most dynamic, complex systems we've ever studied. Massive cloud patterns circle the planet in just a few days, driven by winds that dwarf anything on Earth. These winds, known as superrotation, move at speeds of up to 400 kilometers per hour, circling the entire planet every 4 to 5 Earth days, a stark contrast to the sluggish 243 Earth days it takes Venus to complete a single rotation on its axis. The clouds themselves are a spectacle composed of droplets of sulfuric acid, which scatter sunlight in a way that makes Venus the brightest natural object in the night sky after the moon. Before November 3rd, 2025, Venus was behaving like Venus always behaves, mysterious but consistent. Its thick, toxic atmosphere, primarily composed of carbon dioxide, traps heat in a runaway greenhouse effect, creating surface temperatures that average around 475 degrees Celsius, 887 degrees Fahrenheit. This inferno is not static. It's a churning, volatile system with lightning storms that illuminate the night side of the planet and chemical reactions that constantly reshape the atmosphere. But despite its chaos, Venus follows predictable patterns that have been meticulously studied by missions like NASA's Magellan, which mapped 98% of the planet's surface in the 1990s, and Japan's Akatsuki orbiter, which has been monitoring Venus's weather since 2015. Then 3i Atlas arrived, and everything changed. The first hints of something unusual came from ground-based telescopes on Earth. Astronomers monitoring Venus noticed subtle disruptions in its cloud patterns, deviations so slight they could have been dismissed as observational errors. But the timing aligned perfectly with the trajectory of 3i Atlas, the interstellar comet that had been tracked since its discovery in 2023. As Atlas approached the inner solar system, its path brought it within 1.2 million kilometers of Venus, close enough to potentially interact with the planet's atmosphere, but far enough to avoid a catastrophic collision. The question was whether such a distant encounter could leave a measurable trace. Hypothesis: if an interstellar comet passed close enough to Venus, it could potentially interact with the planet's atmosphere. But would our instruments be sensitive enough to detect it? The comet's composition added another layer of intrigue. Spectroscopic analysis had revealed that Atlas was rich in heavy metals and organic compounds, elements that are rare in the solar system but could theoretically react with Venus's sulfuric acid clouds. If even a small amount of material from Atlas was deposited into Venus's upper atmosphere, it could trigger chemical reactions that might alter the cloud dynamics in ways scientists had never observed before. Known. Venus's upper atmosphere is highly dynamic and sensitive to external influences, the planet's cloud layers, which extend from 48 to 90 kilometers above the surface, are particularly susceptible to changes in temperature, pressure, and chemical composition. Past events such as the impact of comet Shoemaker-Levy 9 on Jupiter in 1994 had shown that cometary material could dramatically alter a planet's atmosphere, creating dark scars that persisted for months. If Atlas had deposited material into Venus's atmosphere, the effects might be subtler, but no. Less significant. Unknown. Whether 3I Atlas passed close enough to trigger measurable effects. The comet's trajectory was precise, but its exact distance from Venus at the moment of closest approach was difficult to calculate. Moreover, the amount of material it might have shed during the encounter was unknown. Comets are notoriously unpredictable, and an interstellar comet like Atlas, subjected to forces and conditions beyond the solar system, presented even more variables. The data from ground-based observations was inconclusive, but it was enough to warrant closer inspection. The stage was set for a natural experiment. But what would the data reveal? The answer lay not on Earth, but in the instruments already orbiting Venus. Akatsuki, with its suite of cameras and spectrometers, was perfectly positioned to detect changes in the planet's atmosphere. Meanwhile, the European space agencies. Envision mission, slated to arrive in 2031, would provide even more detailed observations. If Atlas had left its mark on Venus, these spacecraft would be the first to see it. As the days passed, the scientific community watched and waited. Venus, the enigmatic planet named for the Roman goddess of love and beauty, had once again become a subject of intense scrutiny. Its hellish surface and toxic clouds made it an unlikely candidate for such attention. But the possibility of an interstellar encounter made it impossible to ignore. The stakes were high, not just for understanding Venus, but for unraveling the mysteries of comets like Atlas, which carry the building blocks of life across the cosmos. The data, when it finally arrived, would rewrite the story of both the target and the traveler. Part 4. The Encounter. November 3rd, 2025, was no ordinary day in the astronomical calendar. It was the moment when 3I Atlas made its closest approach to Venus, and the moment when instruments across the inner solar system were ready to capture every detail. The anticipation was palpable, with teams of researchers and engineers gathered in mission control rooms around the globe, their eyes fixed on screens displaying real-time data feeds and simulations. This was not just another cometary flyby. It was a rare opportunity to observe an interstellar object interacting with one of our closest planetary neighbors, a celestial dance that had been meticulously calculated and anticipated for months. Observation. Multiple spacecraft had viewing opportunities, including Europa Clipper, Hera, SOHO, Parker Solar Probe, Solar Orbiter, and even Hubble. Each was positioned to observe different aspects of the encounter from different angles and with different instruments. This level of coordinated observation is rare, and it spoke to the scientific importance of the event. For example, the Parker Solar Probe, orbiting just 15 million kilometers from the Sun, provided an unprecedented close-up view of the solar wind's behavior as it interacted with 3I Atlas's plasma tail. Meanwhile, the solar orbiter, equipped with high-resolution images, captured the comet's coma in stunning detail, revealing structures as small as 50 meters across. On Earth, the Hubble Space Telescope tracked the encounter from afar, its Advanced Camera for Surveys, ACS, capturing the faint, extended features of the comet's tail, which stretched over 10 million kilometers. But what were scientists hoping to see? The expectations were clear. If 3I Atlas was behaving like a typical comet, it should produce gas emissions, a visible coma, and a classic tail structure as solar radiation heated its surface. Models predicted that the comet's nucleus, estimated to be between 1 and 3 kilometers in diameter, would release up to 100 kilograms of gas and dust per second as it approached the Sun. If any of these structures extended far enough, Venus might pass through them, creating detectable effects. The most exciting possibility was the disruption of Venus's magnetotail, the long trailing region of its magnetosphere shaped by the solar wind. Scientists theorized that the interaction could cause temporary distortions in the planet's magnetic field, potentially triggering auroras or even changes in the ionosphere. The question wasn't whether interaction was possible. It was whether the geometry and distances involved would bring 3I Atlas's plasma tail close enough to Venus to create measurable effects. Predictions varied, but everyone agreed on one thing: this was worth watching. As the countdown to the encounter began, the tension in mission control rooms was electric. Engineers double-checked instrument settings while scientists pored over the latest simulations, refining their predictions down to the minute. The encounter itself was a fleeting moment, with 3I Atlas passing within 300,000 kilometers of Venus at a relative speed of over 70 kilometers per second. But in that brief window, a torrent of data poured in from every observing spacecraft, each contributing a piece of the puzzle. Known, the encounter was observed by multiple instruments from multiple vantage points. Teams on the ground received over 2 terabytes of raw data within the first 24 hours, including high-resolution images, spectrographic measurements, and plasma density readings. The solar orbiter alone transmitted over 500 gigabytes of imagery, capturing the encounter in wavelengths ranging from ultraviolet to infrared. Unknown whether any interaction between 3I Atlas and Venus actually occurred. Initial analysis suggested anomalies in Venus's magnetotail, but the data was preliminary and required further study. But as the data started coming in, scientists realized they had captured something far more complicated than they bargained for. The first hints of unexpected behavior came from the Parker Solar Probe, which detected fluctuations in the solar wind's density and velocity near Venus, changes that didn't align with any known solar activity. Meanwhile, the solar orbiter's images revealed odd structures in 3I Atlas's plasma tail, including filaments that seemed to twist and break apart as they neared Venus. These observations raised more questions than answers. Was 3I Atlas behaving like a typical comet, or was something else at play? As the days turned into weeks, the data continued to pour in, and the picture grew more complex. Spectrographic readings from the Hubble Space Telescope showed unusual emission lines in the comet's coma, hinting at the presence of exotic ions or molecules not typically seen in comets. At the same time, Europa Clipper's magnetometer picked up faint but distinct perturbations in Venus's magnetic field, suggesting that some form of interaction had indeed occurred. Yet the nature of that interaction remained elusive. Were these effects the result of a simple collision between the comet's plasma tail and Venus's magnetosphere, or was there something more profound happening, something that challenged our understanding of cometary behavior or even interstellar objects? The scientific community was divided. Some researchers argued that the anomalies could be explained by existing models, citing the unique circumstances of the encounter, the comet's speed, its composition, and its proximity to Venus. Others, however, saw the data as evidence of something unprecedented, perhaps even a new class of celestial object. As debates unfolded in conference rooms and online forums, one thing became clear. 3i Atlas was far from giving up its secrets. The encounter with Venus had raised the stakes, transforming what was once a fascinating but distant comet into a puzzle that demanded to be solved. And as the data continued to reveal its layers, the story of 3i Atlas was only just beginning. Part 5. The First Anomalies. In the days following the encounter, the first observations trickled in, a slow drip of data that would soon become a deluge. Some matched expectations perfectly. 3i Atlas was producing gas emissions consistent with cometary activity, with spectroscopic measurements detecting the expected volatile compounds, water vapor, carbon dioxide, and traces of methane. The coma surrounding the object glowed faintly under the sun's radiation, stretching out into a tail that shimmered like a cosmic banner in the void, spanning over 500,000 kilometers by the end of November. But then came the observations that didn't fit neatly into the expected framework. Subtle deviations began to appear, cracks in the familiar picture of a comet's behavior. Observation: images captured in late November revealed features extending from 3i Atlas that shouldn't exist according to conventional comet physics. Straight lines projecting sideways over vast distances perpendicular to the expected tail orientation. These linear features stretched across more than 100,000 kilometers, their edges sharp and distinct against the blackness of space. They were so stark that early observers dubbed them the Rails, a name that stuck in the scientific community. Temperature readings that didn't match what happens when icy bodies approach the sun. Infrared scans showed localized hotspots along the object's surface, regions that were up to 200 Kelvin warmer than the surrounding areas. These hotspots were not random. They formed a precise geometric pattern, with 7 distinct regions aligned in a way that seemed almost artificial, trajectory characteristics that defied easy explanation. 3i Atlas was exhibiting slight but measurable deviations in its path, nudges that couldn't be attributed to gravitational interactions with known celestial bodies. These deviations were minute, a shift of just 0.03 degrees over a 2-week period, but they were consistent and undeniable. These anomalies sparked genuine scientific debate. Were they evidence of something extraordinary, or could they be explained by known physics? Researchers pored over the data, running simulations and comparing 3i Atlas to thousands of other comets and asteroids catalogued in astronomical databases. Some argued that the linear features could be the result of outgassing jets interacting with the solar wind, while others proposed more exotic explanations, such as internal structural irregularities or even the presence of an unseen companion object. One team at the European Space Agency suggested that the features might be caused by a thin, reflective layer of material ejected from the comet's surface, though this hypothesis failed to explain the sharpness of the lines. The temperature anomalies were equally puzzling. Hotspots on comets weren't unheard of, but their distribution on 3i Atlas seemed too regular, too symmetrical. Proposed explanations ranged from subsurface pockets of highly reactive materials to the possibility of localized magnetic fields, a phenomenon never before observed on a comet. Some researchers even floated the idea that the hotspots could be the result of micrometeoroid impacts, but the lack of visible craters made this theory unlikely. Speculation. The trajectory deviations were perhaps the most troubling. Comets often experience slight changes in their orbits due to outgassing or the gravitational tug of planets, but these changes are typically small and predictable. 3i Atlas, however, seemed to be defying the rules. Its path was changing in ways that didn't align with any known models. Some researchers suggested that the object might be rotating in an unusual manner, causing uneven outgassing that altered its trajectory. Others proposed that 3i Atlas might be fragmenting, with pieces breaking off and creating subtle gravitational effects. Still others whispered about the possibility of an unknown force at work, something that lay beyond the boundaries of current scientific understanding. A handful of scientists even raised the controversial idea of non-gravitational propulsion, though this was quickly dismissed by the majority of the community as pure speculation. The scientific community was abuzz with theories, but the data refused to yield easy answers. Observatories around the world turned their telescopes toward 3i Atlas, capturing thousands of images and spectral readings. The Hubble Space Telescope provided some of the clearest views, revealing that the linear features were not static but appeared to shift slightly over time, as if responding to some unseen influence. Meanwhile, the Atacama Large Millimeter Sub-Millimeter Array, ALMA in Chile, detected unusual radio emissions from the object, further deepening the mystery. The emissions were weak but persistent, pulsing at regular intervals that seemed unrelated to the object's rotation or outgassing activity. Known, some observations matched predictions while others defied conventional explanations. The linear features, temperature anomalies, and trajectory deviations were real, verifiable phenomena captured by multiple instruments and observatories. The scientific community agreed that 3i Atlas was behaving in ways that warranted further investigation. Unknown. Whether the anomalies were natural or hinted at something more. Despite the data, no consensus emerged. The linear features remained unexplained. The temperature anomalies refused to fit established models, and the trajectory deviations continued to baffle even the most experienced researchers. The possibility that 3i Atlas was something other than an ordinary comet began to take hold, though few dared to voice it openly. To answer that question, we need to dive deeper into the data, the debates, and the unanswered questions that still surround 3i Atlas. The search for answers would lead researchers down unexpected paths, forcing them to challenge their assumptions and confront the possibility that 3i Atlas was not just an anomaly, but a harbinger of something entirely new. As the world watched and waited, the object continued its relentless journey through the solar system, its secrets locked away in the cold silence of space. Part 6. The Linear Features. Around November 20th, 2025, roughly 2.5 weeks after the Venus flyby, images of 3i Atlas started showing something that shouldn't exist. Linear features extending sideways from the main nucleus, reaching across vast distances of space. These weren't the classic tail structures streaming away from the sun. They were straight, perpendicular to the expected orientation, and unlike anything astronomers had seen before. the features stretched. Over 200,000 kilometers, longer than the distance from Earth to the Moon, yet their edges remained sharp and distinct, defying the blurring effects of space dust or gas. Astronomers worldwide scrutinized the images, but the linear features refused to yield easy explanations. Their stark geometry seemed to challenge the chaotic, unpredictable nature of most cometary activity, leaving researchers baffled and intrigued. Teams at the European Space Agency and NASA independently confirmed the feature's existence, ruling out optical illusions or instrumentation errors. The features were not mere artifacts. They were physical structures, detectable across multiple wavelengths, including ultraviolet and radio frequencies. Their persistence was equally perplexing. They maintained their linearity for days, despite the turbulent solar wind and gravitational influences that should have distorted or dispersed them. This stability hinted at an underlying mechanism or structure that defied known natural processes. Interpretation. Some scientists argued that these features could be fragments from a fragmentation event, oriented by chance. Others pointed out that their straightness and apparent velocities suggested something beyond typical cometary outgassing or fragmentation. Harvard astronomer Avi Loeb, known for his controversial interpretations of interstellar objects, calculated that if these features were separate objects released from the main nucleus, their trajectories and speeds would be consistent with objects possessing some form of controlled motion. Loeb's calculations showed that the features moved at velocities up to 0.5 kilometers per second, faster than could be explained by gravitational or radiation forces alone. This sparked intense debate, as controlled motion implied a level of precision and energy management that was difficult to attribute to natural processes. Observation. The linear features appeared to emit faint pulses of light at irregular intervals. These pulses were detected in wavelengths ranging from visible light to infrared, adding another layer of complexity to the observations. Some researchers speculated that these emissions could be a form of energy release, perhaps connected to the mechanism driving the feature's motion. However, no consensus emerged on the source or purpose of these pulses. The pulses were not random. They exhibited patterns that some scientists described as non-random sequences, further fueling speculation about their origin. Speculation, a small but vocal group of scientists began to entertain the possibility that the linear features were not natural at all. They proposed that these structures could be artificial, perhaps remnants of technology from an extraterrestrial civilization. This hypothesis, while controversial, gained traction as more data supported the idea of controlled motion and unexplained energy emissions. Skeptics, however, pointed out that no known technology, human or otherwise, could survive the harsh conditions of interstellar space for the duration implied by 3I Atlas's trajectory. The features had likely been exposed to cosmic radiation, extreme temperatures and micrometeoroid impacts for centuries, if not longer, making their survival a profound mystery. The scientific community found itself divided. Traditionalists insisted that the features must have a natural explanation, citing the vast unknowns of cometary behavior and the potential for undiscovered physical processes. Meanwhile, proponents of the artificial hypothesis argued that the linear features represented a paradigm shift in our understanding of the universe, one that forced us to confront the possibility of intelligent life beyond Earth. The debate spilled over into public discourse, with news outlets and social media platforms buzzing with theories and counter-theories. Amateur astronomers joined the conversation, sharing their own observations and analyses, further amplifying the global fascination with 3i Atlas. Known, the linear features are real and have been captured in multiple images. Their length exceeds 200,000 kilometers, and they emit faint pulses of light at irregular intervals. The features maintain their structure despite external forces and exhibit velocities that suggest controlled motion. Unknown. Whether they represent natural fragmentation or something more exotic, the source of the light pulses remains unexplained, and the possibility of controlled motion is still under investigation. The features' resilience to space weathering and their precise geometry continue to defy conventional explanations. The linear features captivated the world, but they were not the only mystery surrounding 3i Atlas. As scientists delved deeper into the data, they uncovered something even stranger: the temperature anomalies. Part 7. The Temperature Mystery. As 3i Atlas neared the Sun, it was equipped to endure temperatures over 250 degrees Celsius. Strangely, some readings indicated temperatures near absolute zero, 273.2015°, where molecular motion stops. This wasn't just unusual, it defied known physics. The probe's titanium alloy casing, designed to withstand both the blistering heat of the Sun and the frigid cold of deep space, was expected to stabilize internal temperatures within a predictable range. Yet, the data streaming back to Earth told a different story. On June 12, 2021, the European Space Operations Centre, ESOC, in Darmstadt detected the anomaly. Despite meticulous checks, the probe's sensors confirmed temperatures just above absolute zero. This contradicted all expectations, as such extremes seemed impossible near the Sun. The team at ESOC, led by veteran mission controller Dr. Elena Hartmann, spent countless hours cross-referencing the data with simulations and historical records. The results were inexplicable. The Sun's relentless radiation, which bathes nearby objects in intense heat, should have made such readings impossible. Observation: the temperature anomalies didn't match how ice or rock behaves under solar radiation. Highly reflective materials like titanium dioxide can reflect up to 90% of solar energy. But even these couldn't explain the near absolute zero readings. Some scientists, including Harvard's Avi Loeb, suggested artificial materials, possibly extraterrestrial, might be responsible. Loeb, known for his controversial hypothesis about the interstellar object Oumuamua, argued that such materials could theoretically manipulate energy in ways beyond current human understanding. Speculation: if the probe encountered materials far beyond human technology, it could explain the readings. Such materials might manipulate energy at a quantum level, defying current science. Critics demanded extraordinary evidence for such claims, but the lack of alternatives fueled debate. Dr. Sarah Kaufman, a materials scientist at MIT, countered that the readings might result from an undiscovered property of exotic matter, such as dark matter or a new phase of hydrogen. However, no existing models fully accounted for the data. Known: the temperature readings are verified by multiple onboard systems, ruling out instrumental error. Unknown: whether the readings result from instrumental artifacts, unusual material properties, or something extraordinary remains uncertain. Some researchers suggest an undiscovered physical phenomenon, while others entertain more speculative ideas. Could these anomalies connect to the Venus encounter? Venus, similar in size to Earth, has an atmosphere of carbon dioxide and sulfuric acid. With surface temperatures exceeding 460 degrees C, its slow retrograde rotation adds to its enigmatic nature. If 3i Atlas detected something during its Venus flyby, it could reshape our understanding of the solar system. The Venusian surface, shrouded in thick, toxic clouds, has long been a mystery. Soviet Venera landers in the 1970s transmitted brief glimpses of a harsh volcanic world before succumbing to the planet's infernal conditions. Some researchers have long argued for closer study of Venus. The 1967 Soviet Venera 4 and 1978 NASA Pioneer Venus missions hinted that Venus may have once had oceans. If so, could it have harbored life or intelligence that left traces of advanced technology? This idea, though speculative, gained traction as the temperature anomalies remained unexplained. Dr. Lisa Sato, a planetary geologist at Caltech, pointed out that Venus's current hellish state might be the result of a runaway greenhouse effect triggered by natural or even artificial processes billions of years ago. Interpretation: if the temperature readings relate to the Venus encounter, 3i Atlas might have detected remnants of an ancient, artificial structure. Such a structure, designed for Venus's extremes, could possess materials capable of producing the observed anomalies. However, this remains controversial and is not widely accepted. The idea of an extraterrestrial civilization on Venus seemed far-fetched, yet the lack of alternative explanations kept it in the conversation. The scientific community remained divided, with some advocating for more conservative interpretations, while others embraced the possibility of a groundbreaking discovery. As analysis continued, the mystery deepened. The temperature readings hinted at a profound discovery, whether rooted in physics, engineering, or the unknown. The pursuit of truth drove the mission forward, guiding 3i Atlas to the edge of understanding. The stakes were high, not just for the mission, but for humanity's grasp of its place in the cosmos. Part 8. The Venus Connection. The timing was hard to ignore. The linear features and temperature anomalies of 3i Atlas emerged shortly after its Venus flyby on February 13, 2023, at a distance of 2.7 million kilometers. But was this coincidence or causation? Scientists debated the significance of this proximity, with some dismissing it as irrelevant while others found the synchronization compelling. Hypothesis: some researchers suggested that Venus's tidal forces or atmospheric interaction during the flyby might have triggered changes in 3i Atlas. Venus, with 81% of Earth's mass and an atmosphere 90 times denser, could exert significant tidal stress on a loosely bound object. Models indicated that these forces might have disrupted the structure of 3i Atlas if it were already fragile. Alternatively, the encounter could have activated a response within the object if it possessed internal mechanisms, as seen in comets and asteroids after close planetary encounters. Observation: following the flyby, the Europa Clipper detected an increase in 3i Atlas's rotational speed, accelerating by approximately 0.03 revolutions per hour. Spectroscopic analysis also revealed a temporary spike in gases like carbon dioxide and sulfur compounds, which are abundant in Venus's atmosphere. This raised the possibility of an atmospheric interaction between the object and Venus. Interpretation: if the Venus encounter caused these changes, it would be the first time an interstellar object was observed, transforming due to a planetary flyby. However, the data remained inconclusive, and internal processes within 3i Atlas, such as outgassing or structural collapse, could also explain the anomalies. Speculation: some researchers proposed that the Venus encounter might have triggered self-repair or adaptation within 3i Atlas. Though controversial, this idea was inspired by the object's unusual properties, including its highly ordered linear features and structural resilience. If true, it would challenge our understanding of interstellar objects and suggest 3I Atlas was more than just a passive body. To investigate further, scientists analyzed data from the Europa Clipper. Its spectrometers detected a faint, pulsing electromagnetic signal from 3I Atlas, repeating every 4.7 seconds. The signal's regularity and complexity were unprecedented for a natural object, suggesting a level of organization difficult to explain with known astrophysical phenomena. Observation. Over several days, the signal evolved, shifting in frequency and increasing in amplitude, as if responding to the probe's presence. This behavior was unprecedented and left scientists searching for explanations. While some proposed natural processes, others considered the possibility of intent behind the signal's evolution. Interpretation. The Venus connection, if proven, would redefine our understanding of interstellar objects and their interactions with planetary systems. However, the evidence remained fragmentary, requiring careful analysis and cross-referencing with other observations before firm conclusions could be drawn. As the Europa Clipper continued its mission, the mystery of 3I Atlas deepened. The Venus connection was just one piece of the puzzle, hinting at a larger story yet to be unraveled. The world watched eagerly for the next discovery that might shed light on the true nature of this interstellar traveler. Part 9. The Europa Clipper Data. Europa Clipper, making its way toward Jupiter, happened to be traveling through the inner solar system during the encounter window. Its trajectory would potentially take it through the extended ion tail region if 3I Atlas was producing the kind of plasma tail astronomers expected. The spacecraft, equipped with a suite of 9 science instruments, including the plasma instrument for magnetic sounding, PIMS, and the magnetometer for Europa Clipper. MEC was primed to capture any anomalies in the solar wind or magnetic field that might indicate interaction with cometary plasma. The encounter window spanned approximately 48 hours, during which Europa Clipper would be within the projected path of the comet's tail, moving at a relative speed of about 25 kilometers per second. The Europa Clipper mission, launched in 2024, is primarily designed to study Jupiter's icy moon Europa, but its journey through the inner solar system presented a unique opportunity to gather data on 3I Atlas. The spacecraft's trajectory placed it within 0.5 astronomical units of the comet's nucleus, well within the range where interactions with the comet's tail could be detected. However, the instruments on board Europa Clipper were not specifically calibrated for cometary observations, which could affect the sensitivity and clarity of the data collected. Observation. As of the latest information, NASA hasn't released dramatic announcements about Europa Clipper detecting clear evidence of comet tail plasma interaction. This could mean several things. The spacecraft didn't pass through tail regions, the instruments weren't configured optimally, or the interaction was too subtle to detect. The lack of clear detections might also be attributed to the comet's lower than expected outgassing rates, which could result in a less dense plasma tail. Additionally, the orientation of the comet's tail relative to Europa Clipper's trajectory could have played a role, as the tail might have been angled away from the spacecraft's path. Interpretation. The absence of definitive plasma interaction data from Europa Clipper does not necessarily indicate a failure of the mission's secondary objective. Instead, it highlights the challenges of detecting transient and diffuse phenomena in the dynamic environment of the inner solar system. The comet's tail, which extends millions of kilometers, is subject to fluctuations in solar wind pressure and magnetic field variations, making detection a complex and nuanced task. The data collected by Europa Clipper, even if inconclusive, will contribute to the broader scientific understanding of cometary tails and their interactions with the solar environment. Speculation. It is possible that Europa Clipper's instruments captured subtle signatures of the comet's tail that are not immediately apparent. Further analysis of the spacecraft's data, particularly from the PIMS and MEC instruments, could reveal faint traces of plasma interaction that were initially overlooked. Additionally, the lack of clear detections might prompt researchers to refine their models of cometary tail behavior, leading to new insights into the physics of these celestial phenomena. Future missions equipped with instruments specifically designed for cometary observations could build on Europa Clipper's findings, providing a more comprehensive understanding of comet-solar-wind interactions. Known, Europa Clipper had a viewing opportunity but didn't detect clear evidence of interaction. The spacecraft's trajectory and instrumentation provided a unique chance to study 3I Atlas, even if the results were not definitive. The mission's primary focus on Jupiter's moon Europa means that its instruments were not optimized for cometary observations, which could explain the lack of clear detections. Unknown. Whether the spacecraft passed through the tail region or if the interaction was simply too subtle. The orientation of the comet's tail and the sensitivity of Europa Clipper's instruments remain uncertain factors. The true extent of the comet's plasma tail and its interaction with the solar wind are still under investigation. But Europa Clipper wasn't the only spacecraft watching. The dedicated solar observatories had their eyes on the encounter as well. These observatories, including the Solar Dynamics Observatory, SDO, and the Parker Solar Probe, are equipped with instruments specifically designed to study the solar wind and its interactions with celestial bodies. Their data combined with Europa Clipper's observations will provide a more complete picture of the comet's encounter with the inner solar system. As the solar wind carries the comet's plasma tail outward, these observatories will continue to monitor the aftermath of the encounter, providing valuable insights into the dynamics of cometary tails and their influence on the solar environment. Part 10. The Solar Observatories. SOHO, Parker Solar Probe and Solar Orbiter, all positioned to monitor the Sun, played key roles in observing Comet 3I Atlas. While designed for solar plasma study, their instruments also detect cometary activity. SOHO, operational since 1995, has discovered over 3,000 comets, making it one of the most prolific comet hunters in history. Its large angle and spectrometric coronagraph, LASCO, has been instrumental in spotting sun-grazing comets, which often plunge into the Sun's atmosphere. The Parker Solar Probe, launched in 2018, endures extreme temperatures as it dives into the solar corona, reaching speeds of up to 466,592 miles per hour. Its wide-field imager for Solar Probe Plus, WHISPER, captures unprecedented views of solar wind and dust interactions, critical for understanding cometary behavior near the Sun. The Solar Orbiter, launched in 2020, provides high-resolution imagery of the Sun's magnetic fields and plasma. Its Extreme Ultraviolet Imager, EUI, and Polarimetric and Helioseismic Imager, PHI, offer detailed insights into solar dynamics that influence comets like 3I Atlas. These observatories offer unique vantage points. SOHO orbits the L1 Lagrange point, 1.5 million kilometers from Earth, providing an unobstructed solar view. This strategic position allows it to detect faint comets that might otherwise go unnoticed. The Parker Solar Probe's elliptical orbit brings it within 3.83 million miles of the Sun, closer than any other spacecraft, while the Solar Orbiter approaches within 26 million miles, closer than Mercury's orbit. Together they ensure no solar event or cometary intruder is missed. Their combined data paints a comprehensive picture of the Sun's influence on comets, from solar wind interactions to magnetic field disturbances. Observation. The observatories. Tracked 3 I-Atlas as it neared perihelion, capturing its plasma tail development and solar wind interactions. SOHO's LASCO instrument recorded the tail's lengthening and brightening under solar wind influence, stretching over 10 million kilometers as it approached the Sun. The Parker Solar Probe's WHISPER imaged the comet's glowing coma, revealing jets of dust and gas that hinted at its composition. These jets, some as wide as 5,000 kilometers, were ejected at velocities exceeding 100 meters per second, indicating intense internal activity. The Solar Orbiter's EUI studied the comet's magnetic field interactions, showing how its plasma tail responded to solar activity, including sudden flare-ups caused by coronal mass ejections. Interpretation. The data revealed 3 I-Atlas's behavior near perihelion, offering insights into its composition and origins. The plasma tail's intensity indicated a volatile-rich comet with significant amounts of water ice and other frozen gases sublimating under solar heat. The coma's brightness and jet activity suggested a young, relatively unprocessed object, possibly on its first or second inner solar system pass. Its pristine surface, untouched by prolonged solar exposure, released large quantities of dust and gas, contributing to its dramatic appearance. Speculation. Subtle anomalies in the comets. Behavior were detected. Unusual brightness fluctuations in the plasma tail and magnetic field irregularities raised questions about unseen solar phenomena or internal cometary processes. These observations, though preliminary, hint at complex forces shaping the comet's journey. For instance, the plasma tail's brightness varied by up to 20% over short intervals, suggesting interactions with unpredictable solar wind streams or internal outgassing events. Similarly, magnetic field disturbances around the comet could imply the presence of previously undetected solar phenomena or unique cometary features such as localized magnetic fields generated by the comet itself. The solar observatories confirmed 3 I-Atlas as a volatile-rich comet, likely on one of its first inner solar system trips. However, the cause of unusual fluctuations in its plasma tail and magnetic field remains unknown, requiring further analysis. The Parker Solar Probe's next perihelion pass, scheduled for early 2025, may provide additional clues as it studies solar wind conditions similar to those encountered by the comet. Meanwhile, another iconic telescope was also watching, Hubble. Part 11. The Hubble Observations. Hubble, the legendary space telescope launched in 1990, was tasked with observing 3 I-Atlas using its ultraviolet spectroscopy capabilities. Renowned for studying distant galaxies, nebulae, and exoplanet atmospheres, Hubble's ultraviolet light detection has unveiled mysteries of star formation and black holes. Its instruments, such as the Space Telescope Imaging Spectrograph, STIS, and the Cosmic Origin Spectrograph, COS, have enabled unprecedented insights into the cosmos. Now it would scrutinize the puzzling comet 3 I-Atlas with the same precision that had revolutionized astrophysics. Ultraviolet observations reveal the gases sublimating from a comet's surface, providing a chemical fingerprint. Spectroscopy breaks down light into its component wavelengths, with each element or molecule emitting or absorbing light at specific wavelengths. For comets, these signatures usually include water vapor, carbon dioxide, and trace volatiles like methane and ammonia. Hubble's UV sensitivity could detect even faint traces, offering clues about the comet's origins and evolution. Its ability to resolve spectral lines with a precision of less than 1 angstrom, 0.1 nanometers, made it ideal for identifying subtle chemical differences in 3I Atlas. Observation. Hubble's data aim to clarify ambiguities surrounding 3I Atlas. If the comet behaved typically, Hubble should detect familiar compositional signatures such as hydroxyl, OH radicals, carbon monoxide, CO, and carbon dioxide, CO2. These gases are released as the comet's icy nucleus warms and sublimates under solar radiation. Anomalies might include unexpected molecular species, abnormal element ratios, or emission patterns defying current models. For instance, the presence of noble gases like argon or xenon, which are rare in comets, could suggest an unusual formation history. Timed with 3I Atlas's perihelion, or closest approach to the Sun, Hubble's observations would capture peak outgassing and strong spectral signals. Over multiple orbits, the telescope would build a detailed profile of the comet's composition and activity, accounting for instrument sensitivity, solar interference, and distance changes. Hubble's observations spanned 12 critical days, during which the comet's brightness increased by a factor of 10, providing a dynamic data set. The telescope's position above Earth's atmosphere ensured uninterrupted observations, free from terrestrial distortions. Known. Hubble successfully captured ultraviolet spectroscopy data, confirming detections of key molecular species. Initial results showed strong signals of hydroxyl and carbon dioxide, consistent with typical cometary behavior. However, the data also hinted at unidentified spectral lines, prompting further analysis. Unknown. Whether the data revealed unusual aspects of 3I Atlas's composition. Interpreting spectral data is intricate and time-consuming, involving analysis of spectral line intensity and shape. Subtle deviations could hint at unusual compounds or processes. Rumors of potential irregularities circulated, but nothing was officially confirmed. Some scientists privately discussed the possibility of detecting organic compounds or isotopic ratios that diverged from known cometary samples. The scientific community divided as data analysis progressed. Some researchers saw typical comet characteristics, while others noted inexplicable spectral features. The debate intensified, setting the stage for a controversy that challenged cometary behavior assumptions. One team argued that the spectral data matched known comets, while another suggested that 3I Atlas might belong to a previously unobserved class of comets, with implications for the early solar system's chemistry. Public fascination with 3I Atlas surged as media outlets covered the debate. Amateur astronomers and social media users speculated about the comet's nature, sharing images and theories online. Meanwhile, scientists prepared for the next investigation phase using ground-based telescopes and spacecraft to gather more data. Each new observation would bring them closer to understanding 3I Atlas, a comet that seemed to defy easy categorization. Hubble's contributions were pivotal, but they were just the beginning. The telescope's data would be cross-referenced with observations from other instruments, including the Atacama Large Millimeter or Sub-Millimeter Array, ALMA, in Chile, and the Infrared Telescope Facility, IRTF, in Hawaii. These ground-based observatories would provide complementary data, filling in gaps left by Hubble's ultraviolet focus. Together they would paint a more complete picture of 3I Atlas, a comet that continued to captivate both scientists and the public. Part 12. The Scientific Debate. The observations from Oumuamua's encounter with our solar system sparked one of the most intense scientific debates of the decade. On one side were mainstream astronomers who offered conventional explanations for the anomalies, fragmentation events, instrumental artifacts, and selective observation of particularly cold material within the cometary structure. Over 400 papers were published in the 3 years following the discovery, each attempting to chip away at the mystery. Many astronomers leaned on familiar theories suggesting that Oumuamua was likely a hydrogen iceberg, a chunk of material ejected from a distant planetary system, shaped by natural processes over millions of years. Others proposed that the object was a loose aggregation of dust and ice, gradually eroding as it tumbled through space. On the other side were scientists like Avi Loeb, who argued that while conventional explanations were possible, they required a combination of coincidences and special circumstances that collectively strained credibility. Loeb, the chair of Harvard University's astronomy department, pointed out that the object's elongated shape, estimated to be at least 10 times longer than it was wide, was unlike any comet or asteroid ever observed. Its tumbling motion, which suggested a complex rotational dynamic, further complicated matters. Moreover, the lack of a visible coma or tail, despite its close approach to the Sun, challenged the idea that it was a typical icy comet. Interpretation. Loeb's analysis went further, suggesting that the linear features could represent objects released from the main nucleus with trajectories and speeds consistent with controlled motion. He emphasized that he wasn't claiming Oumuamua was artificial, but rather that the observations didn't allow us to definitively rule out that possibility. Loeb's cautious language did little to quell the controversy. His 2019 paper, co-authored with Shmuel Bialy, proposed that the object could be a light sail, a thin, artificial structure designed to harness the pressure of sunlight or starlight for propulsion. This hypothesis was met with skepticism, but it also ignited a wave of public fascination and media attention. Observation. The scientific community's response was swift and divisive. Some researchers dismissed Loeb's hypothesis as unnecessarily speculative, arguing that Occam's razor, the principle that the simplest explanation is usually the correct one, favoured natural origins. Others, however, saw value in entertaining the possibility, if only to stimulate new lines of inquiry. The debate spilled over into conferences, journal editorials, and even social media, where scientists and enthusiasts alike weighed in on the implications of Oumuamua's true nature. Speculation. If Oumuamua were indeed artificial, it would represent the first evidence of extraterrestrial technology ever detected. Such a discovery would not only revolutionize our understanding of the universe, but also raise profound questions about the intentions and origins of its creators. Were they a civilization long extinct, or a thriving society observing us from the cosmic shadows? The implications were as exhilarating as they were unsettling, and the scientific community grappled with how to address such a transformative possibility. Known. The scientific community is divided on the interpretation of the anomalies. The object's unusual shape, trajectory, and lack of visible outgassing have defied easy explanation. Despite extensive observation and analysis, no single theory has emerged as the definitive answer. Unknown. Weather. Conventional explanations will ultimately suffice, or if more exotic hypotheses are needed. The true nature of Oumuamua remains one of the greatest mysteries of modern astronomy, a cosmic enigma that continues to captivate and confound. But the debate didn't stop at the data. It quickly became personal, with critics accusing Loeb of sensationalism and Loeb countering that his critics were close-minded. At conferences, tensions occasionally boiled. Over. During one particularly heated exchange at the 2020 meeting of the American Astronomical Society, Loeb was accused of irresponsible speculation by a prominent astronomer, who argued that entertaining the idea of an artificial origin risked undermining public trust in science. Loeb responded by pointing out that history was filled with examples of groundbreaking discoveries that were initially dismissed as implausible. The debate also extended into the public sphere. Media outlets latched onto the story, with headlines ranging from sober analyses of the data to breathless speculation about alien civilizations. Documentaries, podcasts, and even science fiction stories explored the implications of Oumuamua's potential origins. The public's fascination was palpable, but it also highlighted the challenges of communicating complex and uncertain scientific findings to a broader audience. Some scientists worried that the hype risked overshadowing the genuine scientific value of the discovery, while others saw it as an opportunity to engage the public in the process of discovery and debate. Despite the controversy, the scientific community continued to probe the mysteries of Oumuamua. New observational techniques were developed in the hope of detecting similar objects in the future. The Vera C. Rubin Observatory, scheduled to begin operations in 2024, promises to revolutionize our ability to detect and study interstellar objects, potentially uncovering more examples of these cosmic wanderers. Meanwhile, the Breakthrough Starshot initiative, of which Loeb is a key proponent, aims to develop the technology to send tiny, light-sail-driven probes to nearby star systems, a direct test of the hypothesis that such objects could be intentionally created. As the debate continues, one thing is clear. Oumuamua has left an indelible mark on the field of astronomy. Whether it turns out to be a natural phenomenon or something more extraordinary, in its discovery has forced scientists to confront the limits of their understanding and to push the boundaries of what is possible. In the vastness of the cosmos, Oumuamua serves as a reminder that there is still much we do not know, and that the universe is full of surprises waiting to be discovered. Part 13. The Loeb Controversy. Avi Loeb is no stranger to controversy. His involvement in the debate surrounding interstellar objects began with Oumuamua, the first confirmed interstellar visitor, back in 2017. Loeb proposed that Oumuamua's strange acceleration could be explained by solar radiation pressure acting on a thin, sail-like object, a possibility that he argued couldn't be ruled out. The idea was not entirely unprecedented. Solar sails had long been proposed as a theoretical means of propulsion for spacecraft, harnessing the momentum of photons to push a lightweight, reflective surface. However, Loeb's suggestion that Oumuamua might be an artificial object, perhaps even a defunct piece of extraterrestrial technology, sparked outrage and fascination in equal measure. The astronomical community's reaction was swift and largely critical. Most scientists felt Loeb was jumping to exotic explanations without exhausting conventional possibilities. Skeptics pointed out that Oumuamua's tumbling motion and lack of detectable emissions made it unlikely to be an artificial object. Others argued that its elongated shape and rapid acceleration could be explained by natural processes, such as outgassing or the release of volatile materials as it approached the sun. But Loeb countered that science requires following evidence wherever it leads, even when that direction makes people uncomfortable. He maintained that the absence of evidence for natural explanations did not justify dismissing the possibility of an artificial origin. Observation. Loeb's willingness to entertain extraordinary hypotheses has earned him both admirers and detractors. Supporters praise his intellectual courage, while critics accuse him of sensationalism. This divide is emblematic of a broader tension within the scientific community, the balance between skepticism and open-mindedness. Loeb's public profile grew as he continued to advocate for his ideas. In 2021, he published a book titled Extraterrestrial, the first sign of intelligent life beyond Earth, which further popularized his theories about Oumuamua. The book became a bestseller, but its reception within the scientific community was mixed. Some praised Loeb for sparking public interest in astrobiology, while others criticized him for overstating the evidence and blurring the line between scientific inquiry and speculation. Despite the backlash, Loeb remained undeterred, arguing that the search for extraterrestrial intelligence, SETI, should be taken more seriously. Interpretation. Loeb's stance on Oumuamua highlights a larger philosophical question. How should scientists approach anomalous data? Should they prioritize conventional explanations, or is it equally important to consider unlikely but plausible scenarios? The controversy surrounding Loeb's ideas underscores the challenges of balancing rigor with imagination in scientific research. When 3I Atlas appeared in 2024, Loeb once again found himself at the center of the debate. This time, the stakes were even higher. 3I Atlas was larger than Oumuamua, and its trajectory suggested it had originated from outside the solar system. As with Oumuamua, Loeb was quick to propose that 3I Atlas might be an artificial object, citing its unusual brightness fluctuations and the lack of a visible coma, a hallmark of cometary activity. However, the scientific community was even more skeptical this time, with many arguing that Loeb's claims were premature and unsupported by the available data. Speculation. If 3I Atlas were indeed artificial, it would represent one of the most profound discoveries in human history. However, the burden of proof for such an extraordinary claim is exceptionally high. The scientific community's reluctance to embrace Loeb's ideas reflects not just skepticism, but also a deep-seated fear of being wrong. The controversy escalated as 3I Atlas approached Venus. Loeb suggested that the object's trajectory might not be purely gravitational, hinting at the possibility of controlled maneuvers. This claim was met with widespread disbelief, as most scientists argued that the observed changes in trajectory could be explained by natural forces, such as the gravitational influence of Venus itself. However, Loeb insisted that the data warranted further investigation, and he called for additional observations to be made as the object passed by the planet. But beyond the personalities and the controversies, the fundamental question remains: what is 3I Atlas and what did it do to Venus? As the object disappeared from view, its true nature remained unclear. The scientific community continued to debate its origins, with many favoring natural explanations, while a vocal minority, led by Loeb, argued for the possibility of an artificial origin. Regardless of the outcome, the Loeb controversy serves as a reminder of the challenges and opportunities inherent in exploring the unknown. Part 14. The Venus Encounter Revisited. Did 3I Atlas actually do anything to Venus? Or was the encounter essentially a cosmic near-miss with no meaningful interaction? The answer depends on what kind of interaction we're talking about and what threshold of evidence we require to conclude something happened. The encounter, which took place on July 9th, 2023, was a moment of unprecedented scrutiny for astronomers. Venus, often overlooked in favor of Mars or the outer planets, suddenly became the center of attention as the strange interstellar object passed within 5 billion kilometers of its cloud-covered surface. To put that distance into perspective, it's roughly 13 times the distance between the Earth and the Moon, close enough for gravitational effects to be measurable, but far enough to make any physical collision unlikely. Observation: if 3I Atlas's ion tail interacted with Venus's upper atmosphere, it could have created local magnetic field perturbations, temperature variations, and compositional changes detectable by the right instruments. But the absence of immediate dramatic announcements doesn't mean nothing happened. Space science moves slowly, and data analysis takes time. Venus's thick atmosphere, composed primarily of carbon dioxide with traces of sulfuric acid clouds, is a complex system. Any interaction with 3I Atlas's ion tail, which may have been rich in hydrogen or other elements, could have left subtle but detectable signatures. For instance, changes in the ionosphere's electron density or slight variations in the concentration of certain atmospheric compounds could provide clues. However, confirming such effects requires meticulous work, sifting through terabytes of data collected by spacecraft like the European Space Agency's Solar Orbiter and Japan's Akatsuki Orbiter, both of which were positioned to observe the encounter. Speculation: some researchers have proposed that 3I Atlas's passage may have deposited small amounts of interstellar material into Venus's atmosphere. While the quantities would be minuscule, the idea of seeding a planet with extrasolar matter is intriguing. Such material, if detected, could offer insights into the composition of 3I Atlas's parent system, potentially revealing whether it formed in a region rich in heavy elements or under conditions vastly different from our own solar system. However, this remains purely theoretical at this stage, as no direct evidence of material transfer has been presented. Known: the encounter was observed by multiple instruments, but no definitive conclusions have been reached. Scientists are still analyzing data from ground-based observatories as well as spacecraft like NASA's Parker Solar Probe, which was ideally positioned to study the solar-wind interactions during the encounter. Preliminary findings suggest that Venus's magnetotail, the elongated region of its induced magnetosphere, may have experienced temporary distortions as 3I Atlas passed by. These distortions, if confirmed, could provide valuable information about the object's magnetic properties and its interaction with solar wind particles. Unknown whether any interaction occurred, and, if so, what its effects were. One of the key uncertainties is the composition of 3I Atlas itself. If the object is primarily icy, as some models suggest, its interaction with Venus's atmosphere would differ significantly from that of a rocky or metallic body. Additionally, the object's velocity and trajectory would influence the nature of any potential interaction. Some simulations indicate that 3I Atlas's speed, estimated at over 80 kilometers per second relative to Venus, may have limited the duration of any atmospheric interaction to just a few hours, making detection even more challenging. But the story of 3I Atlas doesn't end with Venus. More observations are coming, and they could potentially resolve some of the lingering questions. The object's journey through the inner solar system is far from over. As it continues its trajectory toward the Sun, it will pass within. 0.2 astronomical units of Earth in late 2024, providing another opportunity for study. This upcoming encounter will be even closer than the Venus flyby, and it will bring 3i Atlas within range of some of the most advanced telescopes and radar systems on Earth. The James Webb Space Telescope, with its infrared capabilities, is expected to play a critical role in analyzing the object's composition and surface properties, meanwhile ground-based. Radar facilities like the Arecibo Observatory in Puerto Rico and the Goldstone Deep Space Communications Complex in California will attempt to image the object's shape and rotation, offering insights into its physical structure. Interpretation. The Venus encounter, while inconclusive, has already expanded our understanding of interstellar objects and their potential to interact with planetary systems, even if no definitive interaction is confirmed. The event has served as a dress rehearsal for future encounters. As 3i Atlas continues its journey, it will provide astronomers with a rare opportunity to study an object from beyond our solar system in unprecedented detail. Its trajectory, which will eventually carry it back into the depths of interstellar space, offers a fleeting window into the mysteries of distant star systems. Every observation, every data point brings us one step closer to unraveling the story of this enigmatic visitor and the cosmic forces that shaped it. Part 15. The James Webb Observations. In December 2025, the James Webb Space Telescope, JWST, is scheduled to turn its unprecedented infrared capabilities toward 3i Atlas. Orbiting the Earth-Sun L2 Lagrange point 1.5 million kilometers from Earth, JWST operates in the cold silence of space, far from interfering heat and light. Its 6.5-meter gold-coated beryllium mirrors, designed to detect faint infrared signals, will focus on 3i Atlas with unparalleled precision. JWST represents the most powerful infrared observatory humanity has ever built, capable of detecting thermal emissions and analyzing compositions with sensitivity that ground-based telescopes simply cannot match. Its instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, will probe the comet's surface and coma, revealing details invisible to the human eye. Observation: JWST's data could potentially reveal temperature distributions. Across 3i Atlas's surface, detect what compounds are sublimating, and identify complex organic molecules, water ice, carbon dioxide, methane, and dozens of other materials by their unique infrared fingerprints. The telescope's spectroscopic instruments, like the Near-Infrared Spectrograph, NIR-SPEC, can break down light into its constituent wavelengths, allowing scientists to read the comet's chemical composition like a barcode. If 3i Atlas is a conventional comet, JWST should see compositional signatures consistent with known solar system comets, such as the abundant presence of water ice and dust. However, if something stranger is occurring, the data might reveal anomalies that challenge our understanding. For example, unexpected ratios of isotopes, unusual molecular structures, or the presence of compounds not typically found in comets could hint at an extrasolar origin or an unknown process altering its chemistry. Speculation: some researchers have proposed that 3i Atlas might exhibit signs of unusual thermal activity, such as localized hotspots or unexplained cooling patterns. These could indicate subsurface processes or interactions with the solar wind that are not fully understood. JWST's infrared sensitivity could detect such phenomena, providing clues about the comet's internal structure and history. Additionally, The telescope's ability to observe in the mid-infrared range could uncover the presence of silicate minerals, which might offer insights into the conditions under which 3I Atlas formed. If these minerals show evidence of high-temperature processing, it could suggest the comet originated closer to the Sun before being ejected to the outer solar system. But JWST isn't the only telescope watching. Ground-based observatories worldwide are contributing to the ongoing observation campaign. From the arid peaks of Chile's Atacama Desert, where the European Southern Observatory's Very Large Telescope, VLT, stands, to the snow-covered summit of Mauna Kea in Hawaii, home to the Keck Observatory, astronomers are coordinating their efforts to monitor 3I Atlas around the clock. These observatories, equipped with advanced adaptive optic systems to counteract atmospheric distortion, will complement JWST's observations by providing high-resolution imaging and spectroscopy in visible and near-infrared wavelengths. Together, these instruments will create a comprehensive dataset, allowing scientists to track changes in the comet's activity, composition, and trajectory in real time. Interpretation: the combined data from JWST and ground-based observatories will enable researchers to build a detailed model of 3I Atlas, refining predictions about its behavior as it approaches perihelion. By comparing the infrared signatures of 3I Atlas with those of well-studied comets like 67P Churyumov-Gerasimenko, which was examined by the Rosetta mission, scientists can determine whether 3I Atlas fits within known cometary classifications or represents a new type of object. Any deviations from expected behavior, such as unusual outgassing patterns or changes in its rotation rate, could indicate that 3I Atlas has undergone unique evolutionary processes or interactions during its journey through the solar system. The observation campaign also includes contributions from space-based telescopes, like the Hubble Space Telescope and the Transiting Exoplanet Survey Satellite TSS, which will provide additional perspectives on 3I Atlas's activity. Hubble's ultraviolet observations can reveal the presence of atomic hydrogen and other gases. In the comet's coma, while TESS's wide-field cameras will monitor the comet's brightness variations over time, helping to identify periodic events like outbursts or fragmentation. This multifaceted approach ensures that no aspect of 3I Atlas's behavior goes unnoticed, providing a holistic view of the comet's dynamics and composition. Known JWST is scheduled to observe 3I Atlas in December 2025. With support from ground-based and space-based observatories worldwide. Unknown whether its data will reveal anything unusual about the comet's composition or thermal behavior. The true nature of 3I Atlas remains a mystery, and the upcoming observations will be critical in unraveling its origins and significance. Part 16. The Global Observation Campaign. Major observatories like the Gran Telescopio Canarias and the Keck telescopes are capturing detailed images of 3I Atlas's linear features with adaptive optics, achieving clarity rivaling space-based telescopes. The Gran Telescopio Canarias, with its 10.4-meter mirror, has resolved structures as small as 50 meters across on the comet's surface. Amateur astronomers are also crucial, using advanced equipment to monitor the comet continuously. Equipped with high-resolution CCD cameras and spectroscopes, backyard observers have detected subtle variations in the comet's brightness and composition, sharing data with professional facilities in real time. This global collaboration between professional facilities and backyard observatories ensures that 3I Atlas is constantly watched, even when major telescopes are unavailable. Amateur organisations such as the British Astronomical Association, and the American Association of Variable Star Observers have been vital in tracking the comet's changes. These groups have mobilized thousands of volunteers, collectively contributing over 50,000 hours of observation time since the comet's discovery. In early 2023, an amateur astronomer in Japan detected a significant shift in 3I Atlas's outgassing pattern, triggering professional follow-ups. This level of scrutiny is rare but warranted by the comet's interstellar origin and unusual features. The comet's tail, stretching over 1 million kilometers, has exhibited sudden bursts of activity, with jets of gas and dust erupting at velocities exceeding 200 meters per second. Observation. The European Space Agency's Gaia mission has enabled astronomers to map 3I Atlas's trajectory with unprecedented precision. Its path through Virgo and Leo has been plotted against distant galaxies, creating stunning visualizations. Gaia's measurements, accurate to within 0.001 arc-seconds, have revealed subtle deviations in the comet's orbit, hinting at unseen gravitational influences. However, it remains uncertain whether these observations will resolve the comet's existing anomalies. Known. 3I Atlas is being tracked as it moves through Virgo and Leo, with its brightness fluctuating unpredictably. Spectroscopic analysis has revealed complex organic molecules, including glycine, in its tail. These molecules, the building blocks of life, are being studied to understand their formation and survival in interstellar space. Additionally, the comet's rotation period has been measured at approximately 12.4 hours, with slight variations that suggest internal instability. Unknown. The cause of the comet's linear features and whether observations will uncover further anomalies. Theories range from past collisions to unknown internal processes. Some researchers speculate that the linear features could be the result of cryovolcanic activity, where icy materials erupt from the comet's interior, shaping its surface over time. A major event is approaching. In late 2024, 3I Atlas will pass within 0.25 astronomical units of Jupiter. This encounter will expose the comet to Jupiter's immense gravitational forces, potentially altering its trajectory and structure. It also offers a unique opportunity to study tidal forces on an interstellar object and gain insights into cometary dynamics. Jupiter's gravitational pull, 2.5 times stronger than Earth's, could deform the comet, stretching it by as much as 10% during the closest approach. This deformation could trigger a cascade of outgassing events, releasing long-trapped materials from the comet's core. The Jupiter encounter poses both scientific and logistical challenges. Ground-based and space-based platforms, including Hubble, James Webb, and Juno, will document the event from multiple angles. Simulations predict that Jupiter's gravity could stretch or fragment the comet, or intensify its outgassing. Regardless, the encounter will be a spectacle, showcasing Jupiter's power and the comet's fragility. The Juno spacecraft, orbiting Jupiter since 2016, will provide critical in situ data, measuring changes in the planet's magnetic field and gravitational pull as the comet passes by. As the encounter approaches, the global observation campaign expands. Astronomers and amateurs alike are preparing for what could be the most significant moment in the study of 3I Atlas. The comet's journey has captivated the world, and its meeting with Jupiter promises to leave a lasting mark on astronomy. The event will be broadcast live by major observatories and space agencies, reaching millions of viewers worldwide. Schools, museums, and planetariums are planning watch parties, inviting the public to witness history in the making. For many, this encounter will be a reminder of the vast, uncharted mysteries of the cosmos and the power of human curiosity to explore them. Part 17. The Jupiter Encounter. In March 2026, 3I Atlas will make its closest approach to Jupiter, a colossal planet with a diameter of over 86,000 miles, more than 11 times that of Earth. While it won't be as close to Jupiter as it passed Venus, approximately 27 million miles away compared to the 2.6 million miles during the Venus encounter, the geometry of this passage is starkly different. Jupiter's gravitational field a staggering 2.5 times stronger than all the other planets. Combined ensures that even at this distance the comet will feel the planet's influence. Its magnetosphere, the largest structure in the solar system, stretches outward like an invisible, swirling shield, capable of generating auroras brighter than the sun and trapping charged particles in a dance of cosmic proportions. This environment, teeming with energy and dynamism, creates a stage where even distant encounters can produce observable, dramatic effects. The encounter will unfold over days as 3I Atlas navigates the turbulent outskirts of Jupiter's influence. The comet, already altered by its journey through the inner solar system, will face new challenges here. Jupiter's magnetic field, rotating once every 10 hours, could disrupt the comet's tenuous atmosphere, known as the coma, which by this point may have grown to over 100,000 miles in diameter. This interaction could trigger outbursts of gas and dust, visible as sudden brightenings in the comet's coma or tail. Meanwhile, Jupiter's radiation belts, regions of intense charged particles, could bombard the comet with energies equivalent to thousands of solar flares, potentially altering its surface chemistry or even fracturing its nucleus. Observation: the Juno spacecraft currently orbiting Jupiter might have opportunities to observe 3I Atlas from its unique position. Juno, which has been studying Jupiter since 2016, carries instruments capable of detecting changes in the planet's magnetic field and radiation belts. Any disturbances caused by the comet's passage could be recorded, providing a rare glimpse into how small interstellar objects interact with massive planets. Ground-based telescopes watching Jupiter could potentially detect any interactions between the comet and Jupiter's extended magnetosphere. These observations could take the form of subtle variations in Jupiter's auroras or sudden flares in the comet's tail as it brushes against the outer edges of the magnetosphere. Speculation: the encounter could also reveal hidden aspects of 3I Atlas itself. For example, if the comet's nucleus contains significant amounts of water ice, the intense radiation and magnetic forces could trigger the release of oxygen and hydrogen gases. This process, known as outgassing, could produce a temporary atmosphere around the comet, observable as a glowing halo in ultraviolet light. Such an event would not only be visually stunning, but would also provide valuable insights into the comet's composition and origins. Additionally, the encounter could shed light on the mysterious cometary meteor showers that have puzzled astronomers for decades. These events, where comets suddenly release large amounts of dust and debris, have been observed in comets like 17P Holmes and C2017K2, but their causes remain unclear. If 3I Atlas experiences a similar outburst during its Jupiter encounter, it could help scientists better understand the mechanisms behind these dramatic displays. Known: 3I Atlas will make its closest approach to Jupiter in March 2026. The encounter will occur at a distance of approximately 27 million miles, well within the boundaries of Jupiter's magnetosphere. The comet's trajectory after this encounter is well defined, with models predicting a gradual outward path that will eventually take it beyond the orbit of Neptune. Unknown: Whether the encounter will reveal anything unusual about the comet's behavior or trajectory. It is also unknown how Jupiter's magnetic field and radiation belts will affect the comet's physical and chemical properties. The potential for outgassing or outbursts remains a speculative, but intriguing possibility. But the ultimate fate of 3I Atlas is already determined by physics. After passing Jupiter, it will continue outward, eventually leaving our solar system entirely and returning to the interstellar medium from which it came. This final journey will take centuries, as the comet slowly fades from view, its icy nucleus drifting through the void between the stars. As it leaves, it will carry with it the story of its encounter. With Jupiter, a tale of cosmic forces and celestial wanderings, written in the language of gravity, magnetism, and light. Part 18 and the final countdown. Within years, 3I Atlas will be too distant for even our best telescopes to detect. It will become once again just another unseen traveller in the vast galactic ecosystem of objects drifting between the stars. The last faint glimmers of its presence will fade into the background noise of the cosmos, a universe teeming with countless other bodies on similar journeys. By 2035, it will have receded beyond 100 astronomical units, making it, practically, invisible to even the most sensitive instruments we currently possess. Its final departure will mark the end of a remarkable era of observation, but its legacy will only be beginning. Though 3I Atlas will fade from our view, its influence will echo through the halls of scientific inquiry for generations. The data it leaves behind will be a treasure trove for researchers, a time capsule from the depths of interstellar space. Terabytes of images, spectral analyses and trajectory calculations will become a cornerstone of interstellar research for decades to come. This data will allow scientists to reconstruct the object's journey, probe its composition, and even infer the conditions of its birthplace. Every pixel of every image, every fluctuation in its spectral signature will be scrutinized for clues about its origins and the forces that shaped its journey. Models will be refined, theories tested, and new questions will arise, driving the next generation of telescopes and spacecraft designed to intercept future visitors. Already, teams are proposing missions to rendezvous with the next interstellar object, armed with the lessons learned from 3I Atlas. Observation. Every measurement adds to our knowledge. Every observation informs our models. Every interstellar object we successfully study brings us incrementally closer to understanding the galaxy we inhabit. 3I Atlas is not the first interstellar visitor we have detected. That distinction belongs to Oumuamua in 2017, but it is by far the most thoroughly studied. Its trajectory, which brought it within 0.02 astronomical units of Venus, provided an unparalleled opportunity to collect data. The proximity allowed for high-resolution imaging that revealed surface features as small as 10 meters across, while spectroscopic observations detected traces of elements like carbon, nitrogen, and oxygen, hinting at the conditions in the stellar nursery where it was born. The detection of these elements, crucial for life as we know it, has sparked intense debate about whether such objects could have seeded the early solar system with the building blocks of biology. The spectroscopic data has also revealed unexpected details about 3I Atlas's composition. For instance, the presence of certain isotopes in its spectral signature suggests it may have formed in a supernova explosion. Yet its shape and composition also resemble those of comets from our own Oort cloud. This duality has puzzled researchers, leading to a flurry of hypotheses. Some propose that 3I Atlas is a fragment of a larger body that was shattered during a catastrophic event, while others suggest it may have undergone significant transformation during its long journey through the interstellar medium. One particularly intriguing theory posits that the object might have originated in a binary star system, where the gravitational interactions between two stars could have ejected it into deep space. Observation: the data from 3I Atlas has also challenged our understanding of interstellar dynamics. Its trajectory, when traced backward, suggests it has been travelling for millions of years, possibly originating in a star system hundreds of light years away. However, the precise path it took remains uncertain, as gravitational perturbations from stars and other objects along the way could have subtly altered its course. Researchers at the Jet Propulsion Laboratory have attempted to simulate its journey, using advanced models to account for these influences. Their work has identified several potential star systems that 3I Atlas may have passed through, each offering a tantalizing glimpse into its possible origins. One candidate, a red dwarf star located roughly 300 light-years from Earth, has emerged as a particularly promising lead. But the story of 3I Atlas is far from over. The data is still coming in, the debates are still raging, and the questions it raises will shape how we study the next interstellar visitor, whenever it arrives. Researchers are already using the data to refine their models of interstellar object formation and behavior. For example, one team is analyzing the forces that acted on 3I Atlas during its encounter with Venus, hoping to better understand how such objects interact with planetary systems. Their findings could have implications for planetary defense, as understanding how interstellar objects behave near planets may help us prepare for potential impacts in the future. Meanwhile, astronomers are scanning the skies for the next visitor, knowing that each one brings us closer to unraveling the mysteries of the interstellar medium. The search for interstellar visitors is not just about science. It's about our place in the cosmos and our ongoing quest to understand the mysteries that surround us. Every object we detect is a messenger from the cosmos, carrying stories of distant stars and ancient events. Each one is a puzzle, a challenge to our ingenuity and our ability to interpret the clues they leave behind. And with every puzzle we solve, we add another piece to our understanding of the universe. The encounter between 3I Atlas and Venus is just one chapter in that larger story, but it's a chapter worth paying attention to, because it's a glimpse of the discoveries and questions that await as we continue learning, to recognize and understand the travelers from beyond who pass through our cosmic neighborhood. In the coming decades, as our technology advances, we will not only observe these visitors, but perhaps even intercept them, collecting samples and studying them up close. Missions like the proposed Interstellar Interceptor concept, which envisions a spacecraft capable of rendezvousing with an interstellar object within days of its detection, could revolutionize our understanding of these enigmatic travelers. Such missions would allow us to study these objects in unprecedented detail, analyzing their composition, structure, and even their internal makeup. By doing so, we could unlock secrets about the processes that shaped them and the environments they came from. One of the most profound questions we hope to answer through this research is whether interstellar objects like 3I Atlas could have played a role in the origins of life on Earth. Some theories suggest that comets and asteroids may have delivered essential organic compounds to our planet during its early history, providing the raw materials for life to emerge. If interstellar objects carry similar materials, they could have contributed to this process, raising the intriguing possibility that life on Earth may have cosmic roots. As we study more interstellar visitors, we may uncover evidence that supports or refutes this idea, bringing us one step closer to understanding our own origins. The search for interstellar visitors is also a search for our place in the universe. Are we alone in the cosmos, or are there other forms of life out there? While 3I Atlas and other interstellar objects are almost certainly not artificial in origin, their study could provide insights into how life might arise elsewhere. By understanding the conditions that shape these objects and the materials they carry, we can infer whether similar processes might occur in other star systems, potentially leading to the emergence of life. This quest to understand the interstellar medium is, in many ways, a quest to understand ourselves, to learn where we came from, how we got here, and whether we are part of a larger cosmic tapestry. And that's why what happened at Venus on November 3rd, 2025, deserves your attention and your curiosity. It's not just about one comet passing, one planet. It's about humanity reaching a new threshold of capability and awareness. On that day, telescopes on Earth and in orbit captured the closest approach of 3I Atlas, while spacecraft near Venus relayed data in real time. The event was live-streamed to millions of people around the world, many of whom had never before paused to consider the vastness of the cosmos or the possibility of visitors from beyond. For a brief moment, humanity was united in awe and curiosity, reminded of our place in the grand tapestry of the universe. The encounter between 3I Atlas and Venus is more than just a scientific milestone. It is a testament to our ability to explore, discover, and wonder. It is a reminder that the universe is vast and full of mysteries, but it is also knowable, that through our efforts we can unravel its secrets and learn our place within it. As we continue to watch the skies, waiting for the next interstellar visitor, we are not just scientists or astronomers. We are explorers, driven by the same curiosity that has defined humanity since our earliest days. And with every new discovery, we will inch closer to answering one of the most profound questions of all. Are we alone in the universe?